Hello, my name is Harvie Clark. Welcome to our presentation this afternoon, and well done for sticking with it if you've been watching all afternoon. Thank you to the Davids who went before us. I was interested to hear what you had to say about the potential for new types of windows. So we're going to be talking to you about ventilative cooling in noisy environments and what are practical options for the UK. So Nick is going to be doing most of the talking, but I'm just going to do some introductions. The context of this, of course, is within the AVO guide. So we as acousticians need to start thinking about acoustic conditions when people are using provisions to mitigate overheating. And ventilative cooling is better generally, usually from a sustainability point of view, than mechanical cooling using heat cycles, so air conditioning, for example. So this work has been motivated by our desire to help people deliver sustainable developments, which is balancing comfort with energy performance. So a little bit about Apex Acoustics, where we're coming from. I set it up myself in 2006, working alone, but thankfully we've now grown to become one of the largest independent acoustic consultancies in the UK, with 20 consultants. We took on a graduate in July, which we were very pleased to do, and our London office reopens this week. So we're working out of 3 offices, or 23 offices currently, and we don't just do acoustics anymore, but we also do air quality, air tightness, thermography, and a bit of overheating. If you've seen any of the Association of Noise Consultants Awards, you'll know, or you may know, that we're the only company that's been shortlisted every year in those awards since they began. And we don't always, but we often win awards. And we like to think this is because of our independent approach to the questions. We go back and question what's important about things. We dig a little bit deeper. We don't just do what it says on the tin. And that's where this work has come from too. So Nick is going to give you chapter and verse on ventilative cooling. What is it? How can we understand it? How can we talk to mechanical engineers and develop suitable solutions for sustainable development in this country? Over to you, Nick.
Jack, for the introduction. I'll start with a definition of ventilative cooling. It's not a commonly used term, but it's simply the ventilation which uses ambient or outside air to cool the building. It can be passive or mechanical, or a combination of both, where passive can provide cooling in some conditions, but mechanical assistance is required for the warmest days. How effective it is depends on the temperature outside and the ventilation rate that can be achieved. And the smaller the temperature difference between inside and out, the greater the ventilation rate is required to reduce the internal temperatures by a set amount. So of course it's not effective if the outside temperature is greater than the internal temperatures that you're trying to maintain. The flow rates that can be achieved with passive ventilation depend on the type and size of openings in the facade, the external wind speed and external temperatures. So overall, passive ventilation rates are very variable, whereas a mechanical or a hybrid system can be set to provide a determined flow rate. And why is ventilative cooling considered important? Well, in 2018, we undertook a review of more than 100 large residential planning applications in London and found that 85% of the applications had noise assessments which assumed that the windows were going to be closed, and overheating assessments which assumed that the windows were open. It demonstrated that opening windows was by far the most common method proposed for controlling overheating by the engineers that were undertaking those assessments. But it rarely considered noise levels in combination, and that has led to the development of the AVO guide by the ANC and allows a combined assessment of noise and overheating. About 25% of the overheating assessments did consider noise, and by far the most common solution offered was to provide mechanical ventilative cooling. So when we are considering ventilation openings, We need to be able to define open areas of vents to predict airflow and compare performances between different systems and products. The most intuitive area associated with ventilation openings is the free area, which is the size of the physical opening. However, not only is it ambiguous, as in this image here, is it related to D1 or D2 when you consider louvers, but it doesn't correlate well with the airflow performance, which is a function of both the area and the physical shape, and some shapes are just more aerodynamic than others. So we need a descriptor of a ventilation area that corresponds to airflow characteristics, and we've included a link here to a recent paper which highlights how correct terminology is still a problem within ventilation design, and it recommends appropriate terminology to be used. Equivalent area is a term which may be familiar to some, as it's used to define the airflow characteristics of a trickle vent in Part F. It's defined as the area of a sharp-edged orifice through which air would pass at the same flow rate as the opening under consideration. So for example, when a trickle vent has an equivalent area shown, and 2,500 square millimetres is a common value, then that provides the same aerodynamic performance as a sharp-edged orifice would with an area equal to 2,500 square millimetres. So it's equivalent to it. And finally, the effective area, which in the paper we refer to is recommended as the definition which should be used for ventilation openings. The effective area is labelled as A min in the diagram, and for a simple opening it is calculated from the free area times the coefficient of discharge. Of course, all these items need to be determined through measurements, where you can change the pressure drop and change the flow rate and work it backwards to establish what the coefficient of discharge is and the other parameters. Just a reminder of what is in the current Part F of the building regs. It provides ventilation provision for whole dwelling and moisture extract ventilation, and for systems which use trickle vents it provides the equivalent area of those vents and guidance on where they should be located. The rates required for moisture extract are very unlikely to be sufficient to control overheating. You typically need between 3 and 10 times as much ventilation to control overheating. It can vary greatly. It's both site and building design specific. But I think it's important to understand that the MVHR is very unlikely to be suitable as a solution to control overheating. It doesn't provide sufficient air changes unless it's significantly oversized, and of course in the summer that there is no need for the heat recovery element of that unit, so it doesn't seem like a realistic solution. It can be used and it does get used, but it's probably not the most practical solution. When we look at the acoustic performance of vents, we're all familiar with DNEW, the weighted normalised element level difference, which essentially is the performance of a specific component. So if we have more than one vent, then we need to account for that, and we can do that by calculating the change in performance using the 10 log n. For large events, such as the ones that we're discussing in this assessment, we can apply the same approach based on the area of the vents. So if we double the area, then the performance will be reduced by 3, as though it was the same as having 2 vents. The vents that have been tested for this paper have got an area of 1.8 square meters, so they are large. And then what we can do is we can calculate the area required to control overheating in a particular situation, and we can adjust the acoustic performance of the vents accordingly. So if we need a bigger vent, we can adjust the acoustic performance to represent that. And a summary of the results are here. So we calculated the number of vents that be required to give the ventilation performance equivalent to a 1 square metre simple open window. So an effective area of 0.62 square metres. And that's represented by the sort of second row down where we've got 1 square metre opening. For the vent below that, which we've predicted a performance of 19 dB, DNAW plus CTR, that vent would need to be 600 millimetres long to provide that amount of acoustic performance. And we would need just over 3 units based on the 1.8 square metre size. So to get a 9 dB improvement over a simple 1 square metre opening, you need a significantly bigger attenuation unit. And within the paper we've provided an equation that allows you to predict the volume of the attenuation that may be required if you know what the reduction is that you're looking for and you know what the effective area of the vents is. For comparing the performance of windows, we expect that different styles of windows may be more effective at controlling noise ingress, and we would also expect that different window sizes would be required to provide the same aerodynamic performance. This report by Napier contains a large array of measured sound insulation data for different window types based on different open areas. The open area is reported as a free area, and the largest is 0.2 square metres, which is still fairly small for an open window. It's probably more in line with what you consider as a partially open window rather than a fully open. And to make comparisons between the acoustic performances on a like-for-like basis, we need to be able to establish the airflow performance of the different window configurations. And to do that, there is a discharge coefficient calculator available from the government website. It's provided by the Department for Education, and it had been developed as part of the work to understand overheating in schools. It's freely available to download through the BB101 websites, and so with this tool we can calculate the airflow performance of the open windows based on the geometry of the windows, and then we can adjust the acoustic performance so that we can compare the windows that have the same effective area or the same, will provide the same ventilation rates under equal conditions. So for each of the different window types shown down the left of this table, we calculated the discharge coefficients and hence the effective areas. And over to the right, we've predicted the sound insulation performance of each type of window if it was sized to provide an effective area of 0.62 square metres, which is equivalent to a 1 square metre opening. So you can see that the variation in performance is from 7 to 10 dB, DNAW plus CTR. The predicted value would be 10 dB, DNAW plus CTR. So it's fairly close to what you might predict, and the variation is quite small. I think certainly small enough that you wouldn't want to conclude that one window was particularly better than the other, given some of the uncertainty perhaps surrounding the measurement data of the noise levels and the prediction of the effective areas. So to look at potential solutions, Hilson Moran had undertaken a detailed study of parameters that can influence the potential for overheating for a single bedroom apartment, and they compared the effects of glazing area, vent area, whether they were single or dual aspect, the orientation of the rooms, whether there was internal or external shading, and the effects of thermal mass. This shows a typical arrangement of the rooms which were modelled. It highlights the single and dual aspect arrangements. And for our assessment, we considered dwellings which had a 40% glazed area, which is considered to be the minimum to achieve reasonable daylighting. And we looked at different orientations, established the ventilation openings required to meet the overheating criteria from TM59. The output of the modelling gives the effective areas required, and you can see the highlighted area here shows the smallest effective area that was required in a bedroom in order to meet the criteria of TM59. Now, given that the work we've done earlier on has been based on an effective area of 0.62, then the areas required are equivalent to more than double that, and that's about, so it's around more than 2 square meters of opening, sort of thing you might get from opening double doors onto a balcony or Juliet balcony. So large areas. And I think at this point it's useful to discuss a recent paper that was presented at the SIBSE Technical Symposium, perhaps only last month, and that compared the modelling output from TM59 with some actual performances of buildings, and it found that the modelling overestimated the extent of overheating to some degree. And as acousticians, we're very reliant on others to provide the overheating information, but my experience is that we find varied and varied output, and certainly for similar buildings in the same cities we can get quite different answers in terms of the ventilation rates that are required. And I think the building regulations is intending to bring modelling in as some sort of method of demonstrating compliance to overheating, but I feel that the reason it's certainly behind schedule on that may have something to do with the uncertainty that you get from the models. As completely natural systems seem to be impractical for controlling overheating, particularly in London apartments, where noise levels exceed much above 50 dB LAEQ 8 hours at night, a hybrid system could be considered, which incorporates a facade mounted vent with an integrated fan to provide additional airflow. The refurbishment shown in this case study is on the A12 road in London, and it required a hybrid solution which had quite a small open area of 0.12 square meters for natural ventilation for quite a lot of the time, but it had an integrated fan which could provide the ventilation rates required to purge ventilate the rooms. Overall, the system provided 37 dB reduction from outside to inside, and this is a sketch of the internal layout and the external view of the building shown in the photograph. So to summarise, I'll start with repeating that MVHR is unlikely to be a solution on its own. It generally won't provide sufficient airflow rates that are needed to control overheating, but it may reduce the amount of times that windows need to be opened. Secondly, when we consider the size of passive vents that may be required, there seems to be an unlikely practical solution unless they're used in combination with a mechanical system, and that's certainly been used on several sites. So a smaller vent can be used, and to pull through the airflows that you need, you can use a fan. Thirdly, attenuated vents could be used to reduce the need to open windows in the same way that an MVHR might. So although they may not meet the TM59 criteria alone, the opening of a vent may reduce the need to open windows down to a time period that could be agreeable. So instead of needing to open windows for 2 months, you might only need to open windows for 2 weeks, and that might be seen as acceptable, depending on the noise levels that are outside. And finally, not particularly acoustic related, but I think it's incredibly rare to see buildings change their form to try and introduce mitigation for overheating. It tends to be designed up to a point where the engineers are left to try and come up with a solution, and really it tends to just be looking at different types of glazing and perhaps internal shading. So I think there's perhaps a little bit of a shift needed in the way that building designs are done. So thank you for listening. We're always grateful for questions, and as you probably know, we like to share all the information that we have. So we've put a lot of information on passive ventilative solutions from all parts of the world that you can find on our website at the address shown, or you can go there using the QR code. If you point your camera, it'll select the URL that it reads, or simply just drop us an email. I think we're quite easy to find. So thank you. Bye.